subscribe now and press the bell icon. Never miss an update.
Good morning, student friends. Today I will take the continued part of electrochemistry. So before starting today's program, I will recall what all you have taught in the last session. And we discussed on the electrochemistry is a branch of chemistry which deals mainly with the interconversion of chemical energy into electrical energy or electrical energy into chemical energy. Interconversion. How we can convert the chemical energy into electrical energy or electrical energy into the chemical energy. So the chemical energy into electrical energy is a simple example. I can give you the battery. Most of you are using the mobile battery in the mobiles, and you are the recharging. What is that? They know the chemical reaction takes place, redox reaction takes place, and that chemical energy will be converted to electrical energy. What is a study of electrochemistry? Or the electrical energy can be converted to chemical energy. Suppose I use a source of electric current and I carry out the electrolysis. They are going to manufacture a lot of useful compounds including the metals. So that is the electrical energy into the chemical energy. In the earlier period, you have discussed about the various factors of electrolysis, where you have taken the electricity as a source of energy. Electrical energy has been converted to the chemical energy. You have studied about the electrolytes. So what are the of electrolysis you have studied, and you have illustrated the Faraday's laws of electrolysis. And even the terms used to measure the electronic conductance, specific conductance, equivalent conductance, molar conductance, degree of dissociation, even ionic mobility. How ionic mobility can be used, that is the correlation of ionic mobilities. That all you have discussed in the last period, in the earlier period. Today, on second part of electrochemistry, so I have written electrochemistry will continue. I have written. I will take up the conversion of chemical energy into electrical energy. How chemical energy can be converted to electrical energy? We are going to use electrochemical cell, or electrochemical cell is called a galvanic cell, or voltaic cell, or radial cell. Then what is the origin of the electrochemical cell? How the chemical energy can be converted to electrical energy? What is the origin of EMF of a cell? I will explain today. So to begin with, I will define what is meant by a single electrode potential. It is called the single electrode potential. Single electrode potential is you take any metal rod. You can take any metal rod, dip it into a solution containing its own ions. So any metal rod can be dipped into a metallic salt solution containing its own ions. Look at the example. I have taken the zinc rod. I have taken zinc rod. So dip it into ZnSO4 solution. This is the zinc rod I have taken. So this zinc rod solid is in contact with its own ions, so Zn2 plus ions. At the interface or junction of the metal and ions, a potential is developed. There is a small amount of electric current is developed. That is called the single electrode potential. You can take any metal rod. Putting any metal rod, dip it into a metallic salt solution containing its own ions. See, zinc rod dipped into Zn2 plus ion. At the interface of the metal and the solution, a small amount of current because the potential is developed, and that is called the single electrode potential. What is the mechanism? How does this the potential arises? I'll give the mechanism based on the Helmholtz. This is called the Helmholtz electrical double layer theory. Helmholtz electrical double layer theory. So I have taken the example of the zinc rod I have taken, dipped into the zinc sulfate solution. So zinc is a more active metal. I will take the concept of electrochemical series. Zinc is placed above the hydrogen. Zinc is more active, means more tendency to lose electron. So when this zinc rod is dipped in zinc sulfate solution, so zinc has got more tendency to dissolve. So more tendency to lose electron. So this zinc rod on dipped solution, so decomposes into, so it dissolves into Zn2 plus ions and liberating electrons. What happens these Zn2 plus ions? These Zn2 plus ions will go into the solution. But what will happen to the electrons? The electrons will left on the metal rod. Look at the mechanism. Zinc rod is a more active metal, more tendency to dissolve, or more tendency to lose electron. Zinc rod dissolves, forming Zn2 plus ions. So these N2 plus ions you go into the solution. But what will happen to these electrons? Electrons are not moving into the solution. They accumulates in the metal rod. Imagine after some time what will happen. So this rod become rich in electrons. You can see negative layer of electrons can be seen in the zinc rod. Zinc is a more, you understand the basic concept in the construction of electrochemical cell. Zinc rod is a more active metal dipped in its own ions. Zinc has got more tendency to lose electrons. So this zinc rod more tendency to lose electron dissolving in Zn2 plus ions. So these Zn2 plus ions are moving into the solution, but electrons accumulate in the metal rod. After some time, this rod becomes rich in the electron. So this rod becomes rich in electron. It develops a negative potential. So this has been due to the rich in electrons. I give the negative potential. Zinc undergoes the oxidation, loss of electron. It undergoes oxidation. I call the zinc electrode as the anode. Zinc undergoes oxidation, so we call it the anode. In the case of electrolysis, anode is positive, but here is anode is negative because the accumulation of so the excess of electrons in the metal rod. What happens is these negative electrons attracts Zn2 plus in the solution. This negative layer of electrons attracts the Zn2 plus ions in this solution. So you can see the formation of an electrical double layer is formed. And this electrical double layer is called the Helmholtz electrical double layer. Okay, zinc rod is dipped in its solution in its own ions. Zinc undergoes oxidation, liberating electrons. So this electrons accumulates in the metal rod, and this the negative electrons attracts the Zn2 plus ions in the solution. Attract Zn2 plus ions. You can see inside negative layer of negative charges, outside a layer of positive charges. It's called the electrical double layer. Because of this electrical double layer, a potential is developed. That is called a single electrode. It's a very important concept. Before going to the construction of electrochemical cell, you must know what is meant by a single electrode potential. I will now define what is meant by a single electrode potential. Any metal rod dipped into a metallic salt solution containing its own ions at the interface of the metal and the solution. A potential or a small amount of current because the potential is developed. So due to the Helmholtz electrical double layer, that is called single electrode potential. I will take the zinc as an example, which is placed above the electrochemical series. More tendency to lose electron, it undergoes oxidation. So I call it as anode, but the charge is negative because the accumulation negative charge of electron. I give the charge as the negative. So this is the single electrode potential. I will take another example. I will take the copper rod dipped into Cu2 plus dipped into copper sulfate solution. The copper is placed there below the hydrogen in the electrochemical series. So lesser tendency to lose electrons or more tendency to undergo reduction, lesser tendency to lose electron. Here what happens now the zinc rod is dipped into this copper rod is dipped into copper sulfate solution, and this the copper ions. So because this is lesser tendency to oxidation, more tendency to undergo reduction, the Cu2 plus ions of the solution, but it takes up the electrons from the metal rod, and the copper will get deposited on the metal rod. Or sometimes what happens? So this zinc rod is losing the electrons, become deficiency in this electron, it develops a positive potential. Look at this. So this is the Cu2 plus ions takes up electrons from the copper rod, and copper is deposited. It's very simple. You get the copper rod dipped into copper sulfate solution. After 5 minutes, you can see a deposit of the copper, metallic copper on the copper rod, because this has got more tendency to undergo reduction, lesser tendency to lose electrons. That's why the Cu2 plus ions in the solution accept electrons from the metal rod, and the copper is deposited. As the process continues, since Cu2 plus ions takes up more and more electrons from the metal rod will become deficient in electrons. That's why the layer of the positive charges. So these positive charges, so the attraction of the SO4 2 minus ion in the solution contains SO4 2 minus ion. It attracts the negative SO4 2 minus ion. Again, there is a formation of double layer, more electrical double layer. A potential is developed. That is called a single electrode potential. So two examples are taken. Only the more active metal are taken, less active metal are taken. More active metal, which has more tendency to lose electron, so this lesser tendency to lose electron. More tendency to lose electron undergoes oxidation, they call the anode. Because of more electrons, this becomes a negative charge. And this copper rod has got lesser tendency to lose electron, undergoes reduction, I given as the cathode. Because deficiency of electron become a positive charge, I get the positive charge. To construct a galvanic cell, you cannot take zinc rod and zinc rod. You take metals of different activity. You place one metal placed above the addition, one metal placed below the addition. We can construct an electrochemical cell. So electrochemical cell or galvanic cell is a device which converts chemical energy into electrical energy. How we can convert? Now only a small amount of potential has been developed, So this we cannot produce the electrical energy. You have to convert a galvanic cell or an electrochemical cell. To consider a galvanic cell, what I will do is I will use a salt bridge. It is a U-shaped glass tube containing potassium chloride solution. It is a U-shaped glass tube. So this is called a salt bridge. I will use a salt bridge. This contains potassium chloride solution. It gives electrical contact between the two opposites. This is the salt bridge. So this salt bridge is containing the potassium. This is the salt bridge. Salt bridge containing the potassium chloride solution. It gives the electrical contact between the two opposites. So this is a single electrode, single electrode. We cannot produce electric current. You have to form a cell. So these two single electrodes are combined internally by using a salt bridge which contains potassium chloride solution. And externally, I will connect to a volt and keep a voltmeter. I will connect to a voltmeter. You can see the current flows in the outer circuit. Current flows in the outer circuit. What is the direction of flow of current? The current was found to be flowing from cathode. This is the flow of current. Direction of the flow of current. So this is the flow of current. The current was found to be flowing towards the cathode to anode. Why the current flows in the outer circuit? Because of the potential difference between the two electrodes. That potential difference between the two electrodes is called the electromotive force of a cell. So EMF of a cell is the potential difference between the two electrodes. Means the potential difference between the cathode and the anode. Why you have taken this potential difference? Because the current flows from cathode to anode. And this potential difference between cathode and anode is called the electromotive force of a cell or EMF of a galvanic cell. But I have taken two single electrodes I have taken. One is more reactive, less reactive. So internally I connected through a salt bridge and externally through a voltmeter. We can see the current flows in the outer circuit. That too current was going to be flowing from cathode to the anode. Why the current flows in the outer circuit? Because of the potential difference between the two electrodes. That too current was going to be flowing from cathode to the anode. And this is called the electromotive force. This potential difference between the cathode and anode is called the electromotive force of a cell. The current flows from the cathode and what the direction flow of electrons. So the flow of electrons will be the opposite direction. What the flow of electrons? Flow of electrons. Here so this electrons are traveling outer circuit to the cathode where it goes reduction. Where the current is flowing from the cathode to the anode. And this potential difference between the two electrodes is called the electromotive force of a cell. And this divide is called as a electrochemical cell. Generally, we call it a galvanic cell, we call it as a voltaic cell, or it is called as a Nernst cell. Look at this very important concept you have to understand. The galvanic cell is a device which converts chemical energy into electrical energy. That means you have to design a redox reaction to occur. Then the redox reaction takes place and chemical energy will become electrical energy. That's why I have taken the two single electrodes I have taken. So one electrode undergoes oxidation, one zinc electrode undergoes oxidation, negative, acts as anode. So this undergoes reduction, I call the cathode, a positive. So these two single electrodes, they have been combined to form a cell. And that cell is called a galvanic cell or a radial cell or voltaic cell. In generally we call it an electrochemical cell. So these two, so single electrodes. So these two single electrodes have been combined to form a cell, we call it the off cell and off cell. Two off cells are combined to form an electrochemical cell. And current was found to be flowing from the cathode to the anode. And this potential difference between the cathode and anode is called the electromotive force of a cell. So this is the origin of the electromotive force of a cell. And then I will explain clearly what is the function of a salt bridge. So this salt bridge is used. See, you have studied electrolysis in the earlier chapter, and you have not used any salt bridge. So electrodes are dipped into the same solution, and you have studied the migration of current and reaction occurring in the anode and cathode. Here the two half cells or two single electrodes are connected by the short bridge, a U-shaped glass tube containing potassium chloride. And this short bridge gives the internal contact between the two half cells. One function is mainly gives the internal contact between the two half cells. One function. Other will be it maintains the liquid junction potential. Suppose I mix the Zn2 plus Ar is in contact Cu2 plus Ar. At the junction again the potential arises. It's interfering in the measurements. Thus we are separating the Zn2 plus and copper 2 plus by using a short bridge. So this short bridge eliminates the liquid junction potential. Suppose if you mix so these two solutions, again there is a potential arises. That's why this short bridge mainly eliminates the liquid junction potential. Other important function is it maintains the electrical neutrality. What is meant by electrical neutrality? Look at this here. So this is the negative layer of electrons and this is the positive. The electrical double layer is there. Suppose if positive ions are there, so these electrons cannot move freely. So these positive charges has to be neutralized. Then what happens? The Cl minus or Cl minus ions of the short bridge, it move and neutralizes these charges, and thereby it causes the flow movement of the electron. Similarly, here the K plus. So K plus ions of the short bridge, it moves and it neutralizes the negative charges, and thereby the flow of current will be easier. It is called electrical neutrality. So this accumulation of positive charges are theoretically removed by Cl minus ions of the short bridge. So this is the K plus SO4 or KPSO4 is formed this potassium ion. So neutralizes the negative charges, thereby there is a continuous flow of electrons current will take place, and therefore this the galvanic cell is a spontaneous reaction. It is a spontaneous cell. When once we construct the cell, the reaction taking place on its own, unlike the electrolytic cell. The electrolytic cell, so current is a source. If you remove the current, the reaction stops. But here once we initiated, this reaction will keep on taking place. So this galvanic cell is a spontaneous. That's why short bridge is mainly used to give the electrical contact between the two half cells. It eliminates the liquid junction potential. It also maintains the electrical neutrality between the two functions of the short bridge. And overall, there is a specific rules to represent the galvanic cell. How to represent? UPSC has given the methodology to represent a galvanic cell. Look here, represent a galvanic cell. So this is the taken the zinc rod is in contact with Zn2 plus ion. But a salt bridge is in contact with the SO4. This is contact with Cu2 plus ion is in contact with copper. Look at this cell you have taken. Zinc rod, zinc ions, salt bridge, copper ions, and copper rod. So this undergoes oxidation, this undergoes the reduction. As per the UPSC convention, oxidation of cell should be written at the left hand side. But the zinc rod, zinc in contact with Zn2 plus, this is the oxidation of cell. So this should be written on the left hand side. Right, reduction of cell, but this is the copper sulfate and copper reduction is actually cathode, written on the right hand side. That's why this is the two vertical lines. Between the two options indicate a short bridge. In all electrochemical cell, we are going to write the two vertical lines. So these vertical lines indicates the short bridge. But the oxidation of cell, reduction of cell, these two options are connected internally by using a short bridge. This is the UPSC system of representing electrochemical cell. Number of numerical will appear in your examination. You will give representation of electrochemical cell. You must know this is oxidation of cell. So this is means LHS. Left hand side is always oxidation of cell. Right hand side is reduction of cell. So these two cells are connected internally by using a short bridge. Now current flows from cathode to the anode. Or the potential difference between the cathode and anode, or potential difference between the right hand side electrode and the left hand side. That's why EMF of chaos of different as well. E right minus E left. Cathode is on the right side, anode is on the left side. Oxidation of cell should be the left hand side. So reduction of cell is on the right hand side. E right minus E left. Cathode minus anode is called the electrochemical cell. That is called the galvanic cell. So this is the representation of a galvanic cell here. So this galvanic cell has to be represented systematically. Whenever if you want to write a galvanic cell, if you ask to write a galvanic cell, oxidation of cell should be written. We have shown zinc undergoes oxidation. This is called oxidation of cell. In this particular example, for zinc loses electron. This is called oxidation of cell. The copper Cu2 plus ions accepts electron and the copper. This is a reduction of cell. So this is the at this location 2 electrons are produced and consumed. So overall reaction of zinc undergoes oxidation. Copper ions are reduced to copper. So this redox reaction takes place, and chemical energy will convert to electrical energy, and that is called EMF of a cell. So based on the direction of flow of current, we define the electromotive force of a cell as the potential difference between the cathode and the anode, or potential difference between the right hand side electrode and left hand side electrode is called EMF of a galvanic cell. I given the single electrode potential. So then they what the function of short bridge, and that is what the electrical double layer. Whenever any metal rod can take, zinc rod, copper rod, iron rod, aluminum rod, any metal rod dipped into a metallic salt solution carrying its own ions. At the junction or at the interface of the metal and the solution, a small amount of current is developed. It's got a potential is developed there, and that potential is called a single electrode potential. So if you want to construct a cell, we require two electrodes. One has to undergo oxidation, one must undergo reduction. We have used the application of the electrochemical cell. We choose one metal placed above the hydrogen, one metal placed below the hydrogen. You form an electrochemical cell. So this is more active metal or less active metal. So this oxidation, this undergoes oxidation, this undergoes reduction. To combine these two internally by using a salt bridge and externally through a copper wire. But you can observe current flows in the outer circuit from the cathode to the anode. This is the flow of current. So why the current flows? Because of the potential difference between the two electrodes, and the potential difference between the two electrodes is called the electromotive force of a cell. Is defined as potential difference between the cathode and the anode. As per the IUPAC cell condition, as I told you, oxidation of cell should be written on the right hand side. Reduction of cells written on the right hand side. Current flows from the cathode to anode. So the difference between E right minus E left. I give the other modern definition. EMF is equal to E right, potential of the right hand side electrode, minus potential of the left hand side electrode. We use the electromotive force of a cell. By based on the consider the concept of single electrode potential. I explained how the chemical energy can be converted into electrical energy based on the single electrode potential. So single electrode potential, you have to construct the two single electrodes. Or you can two off cells should be combined to form a one cell. It's called an electrochemical cell or a galvanic cell. Always any galvanic cell, current flows from cathode to the anode. And that potential difference between the two electrodes is taken as the electromotive force, since that is the origin of the EMF of a cell. Friends, okay, I will introduce one more term called the standard electrode potential. But I give the single electrode potential. What is meant by standard electrode potential? Single electrode potential is like take any metal rod, can be dipped into any metallic salt solution of any given concentration, at any given temperature, at any given pressure. This is called the standard, this is called a single electrode potential. Any metal rod dipped into metallic salt solution containing its own ions at any given concentration, at any given temperature, pressure, we call a single electrode potential. If you say standard electrode potential means the metal rod should be dipped into metallic salt solution of 1 molar concentration at 25 degrees centigrade and 1 atmospheric pressure is called the standard electrode potential, and this value is constant for the given electrode. So difference between single electrode potential and standard electrode potential. Single electrode potential is you can take the metal rod, dipped into a metallic salt solution of any given concentration at any given condition, temperature and pressure. If it is standard means, so this metal rod should be dipped into a metallic salt solution of only 1 molar concentration. 298 Kelvin, 1 atmosphere pressure, 101.3 kilopascal pressure. The potential thus developed is called the standard electrode potential, and this value is constant for the given electrode. So we will take an example of the E naught of the E naught of zinc was found to be minus 0.76 volts. This is constant for the given electrode. Or take the copper of the E naught of copper of the was found to be equal to plus 0.34 volts. So this is constant for the given electrode. Called single electrode potential. Single electrode under laboratory condition, you get the any solution concentration at any given temperature, pressure, you can measure the potential is called a single electrode potential. If it is a standard, the metal rod should be dipped in a metallic salt solution of 1 molar concentration at 25 degrees centigrade, 1 atmospheric pressure, and the potential thus developed at the interface of the metal and the solution is called the standard electrode potential. I repeat again. So in this electrode, 2 electrodes has been taken, 2 single electrodes. Now if here upwards I call as off cell. What is off cell? Off cell. 2 off cells have been combined for one complete cell. I use so U-shaped glass tube containing potassium chloride, which is used as electrolyte, as a filling solution. And this sorbent gives the electrical contact between the 2 off cells. It eliminates the liquid junction potential, and also it maintains the electrical neutrality between the 2 off cells. So for that phenomena, we are going to use a sorbent in any electrochemical cell. So current actually create copper wire. You can see in any electrochemical cell, current was found to be flowing from the cathode to the anode. It's a very convention. If you want to see when a cell has been constructed, you don't know which is anode, which is cathode. You have to see what is the direction of flow of current. Always current flows from the cathode to the anode. By seeing the direction of flow of current, we can assign the charges on the electrode, which becomes cathode, which becomes anode. In all electrochemical cells, so current flows from the cathode to the anode. And this potential difference between the 2 electrodes is taken as the electromotive force of the cell. As per the modern definition, so EMF can be defined as potential difference between the right hand side electrode and left hand side electrode. It's called the electrochemical cell or galvanic cell. So there is a device used to convert the chemical energy into electricity. Students can understand. It's a very basic concept. I explained everything. I use the course for the electrical Helmholtz electrical double layer. Whenever any metal rod, metallic salt solution, potential develops. How potential develops? There is a electrical double inside negative charges, outside positive charges. In the zinc, here the copper, inside positive charges, outside negative charges. Because of electrical double layer, a potential is developed at the interface of the metal and the solution, and we call it a single electrode potential. If the metal rod dipped into 1 molar concentration, 25 degree 1 atmosphere, we call it the standard electrode potential. So most important is, so this is the one electron undergoes oxidation, other undergoes reduction. So the net cell reaction takes place and chemical energy will convert to electrical energy. And we have to use the IUPAC cell convention to write any electrochemical cell. The oxidation of cell should be written on the left hand side. Reduction of cells should be written on the right hand side. So the E right minus E left will give you the electromotive because this is a flow of current. Current flowing from the cathode to the anode. So this potential difference between these 2 electrodes is called the electromotive force of a galvanic cell. That is the origin of EMF of a galvanic cell. Okay friends? Okay. I'll continue. I'll come to another part. Students, I will explain you how to measure the single electrode potential. Single electrode potential can be measured by using the Nernst equation. And this Nernst equation has been derived based on the thermodynamic consideration, and that derivation is not there in your NCERT syllabus. I will directly assume the equation, and I will explain you how to use the application of the Nernst equation. So this is I have taken a simple metal ion undergoes taken reduction potential. I have taken metal ion undergoes reduction to metal solid. So this is the oxidized form. So this is taken a single electrode potential. How we can use the Nernst equation to calculate the single electrode potential. So like this, the metal. So this is say I have taken any metal ion undergoes reduction, get reduced to metal. So this is the oxidized form and this is the reduced form. So now I told I am not going to give the derivation. So on the basis of thermodynamic consideration, this equation has been derived. Now directly assume the Nernst equation. Now E is equal to E naught minus 2.303 RT over NF log to the base 10 of reduced form concentration to the oxidized form. reduced foreign concentration, the oxidized foreign concentration. Look at the equation. E is called the single electrode potential, and E naught is called the standard electrode potential. I give the difference. Single electrode potential or standard electrode potential. R is the gas constant, that is 8.314 joule per Kelvin per mole. Temperature is Kelvin. F is the Faraday, that is 96,500 coulombs. N is the number of moles of electrons transferred, or the valency of AR, or number of moles of electrons transferred N. So reduced foreign concentration to the oxidation foreign concentration. The same equation, reduced foreign concentration means you take metal concentration. So this oxidation foreign is for the metal ion concentration. So this is the reduced form is metal concentration. This is the metal concentration, and this metal ion concentration. Take the metal concentration, metal ion concentration. By convention, the concentration of metal, any solid substance is taken as unity. As you know, the concentration of any metal, any solid substance, even the concentration of any metal is taken as unity. So this metal is taken as one again. This is the metal ion. So this is the metal ion concentration. E is equal to single electrode potential, standard electrode potential, 2.303 RT over enough, log to the base number 1 upon the metal ion concentration. So this is the equation 1 diagram. Suppose I will give simplified form of the first equation. We know the value of R, we know the value of F. Suppose I have T, I will take 25 degrees centigrade, 298 Kelvin. Substitute all these values except the N, So all these values are same except the N. So except the N, all the values are known for us. Therefore, it is 2.303 RT. This F becomes equal to 0.059 N log to the base 1 upon metal ion concentration is the simplified form of the first equation. Why I am giving this equation is all these equations are used to solve the numericals. Some simple numericals for the board examination, some complex numericals in the national competitive examination. So this is the if the temperature is other than 298, you cannot use this equation. If temperature is taken as 298 Kelvin, I give the simplified form of the equation. If temperature is different, use this equation 2.303 RT over enough log to the pressure put upon metal ion concentration. I have taken the metal rod, dipped into a metallic salt solution of no concentration. That is the metal concentration is taken as 1. Metal ion concentration, the E naught value is a constant for the given electrode. The single electrode potential can be calculated. Nernst equation is used to calculate single electrode potential. E naught is for standard electrode potential. I defined already. Standard electrode potential means the metal rod should be dipped into metallic salt solution of 1 molar concentration, 25 degrees centigrade, 1 at constant pressure. So which is constant for the given electrode. I told you only taken the zinc as an example. It values for the minus 0.76 volts. So this is constant for the given electrode. E is equal to E naught. So this value is 2.303 RT log to the base 1 upon metal ion concentration. Based on the metal ion concentration, you will get the value of the single electrode potential. So thus the equation can be used to calculate the single electrode potential. Okay, students. Okay, I'll come to the Nernst equation for EMF of a cell. A cell has been constructed. A cell has been constructed, and here you measure the EMF area. How to apply Nernst equation for the EMF of a cell? The same equation. The same equation I will use for a cell. So instead of electrode, I will take a cell here. I will use the known E cell. I will consider a reversible redox reaction. So to write the equation for the EMF of a cell, that's the equation. I will consider a redox reaction on E small a capital A, B small c capital C, small d capital B. For A, B are the reactants, as you know. C and D are the products. So the small letters A, B, C, D represent the concentration terms or stoichiometric coefficients. So this is the equation. I will write the first equation for the E cell. Same equation. The same which I put for the cell is the E cell. Put E naught cell, standard EMF of the cell, 2.303 RT over NF. So as per the law at equilibrium, if you apply the law of mass action for the product of the active mass of the products, So the C to the power of C, D to the power of D. So the product active mass of the reactants where the concentration terms are raised to the power. That is studied on the equilibrium constant. So this is the ratio of the product of the active mass of the products to the product of the active mass of the reactants and raised to the power thereof in the concentration terms. So at equilibrium, so this can be taken as the case equilibrium constant. Therefore the E cell is equal to E naught cell 2.303 RT1 log to the base of Kc, where Kc is for the equilibrium constant. Again, if you take the temperature as 298 Kelvin, substituting all the values, you can simplify the equation. E cell is equal to E naught cell minus 0.059 N log to the base of Kc. The equilibrium constant, standard EMF of the cell. So the EMF of the E cell, given cell can be calculated using the Nernst equation. So Nernst equation for a single electrode. Nernst equation for the EMF of the cell. All these equations we are widely used in number of numerical calculations. EMF of the cell is equal to E naught of cell is called the standard EMF of the cell, which is constant for the given electrode 2.303 R gas constant, T temperature Kelvin, F is the Faraday, 96,500 coulombs. N is the number of moles of electron transfer, is a valency of K. So this should be taken as an equilibrium constant case. By knowing the at equilibrium, by knowing equilibrium constant of a reversible redox reaction, knowing the E naught of cell, so the EMF of a given cell can be calculated using the Nernst equation. So this is the Nernst equation for the EMF of a cell. Nernst equation for a single electrode potential. Nernst equation for an EMF of a cell, because two electrodes has been combined. Two off cell has been combined to form a cell, electrochemical cell. So EMF the electrochemical cell can be given by the Nernst equation. Another form. These are various forms of the Nernst equation. One more concept, take the relationship between standard free energy and standard EMF of the cell, delta G naught. So for standard free energy and standard EMF of the cell. You know what is the free energy? Free energy is the capacity of the system to perform work. Is a measure of available energy which can be converted to useful work. Whenever a redox chemical reaction takes place and chemical energy is converted to electrical energy, what happens to the free energy? The free energy decreases. The work is done at the cost of the free energy. Look at the equation. I given so minus delta G is equal to W. In any electrochemical reaction, work is done at the cost of the free energy decreases. Well, what if in this equation delta G is equal to minus W? Work done. So doing a electrochemical reaction is given by N F E naught of cell. N is the number of moles of electron transfer. F is called the Faraday. E naught cell equals standard EMF of the cell. And free energy, so can be calculated. The free energy can be calculated. This is what work done. How much work done on the electrochemical means we calculate the free energy. Decrease the free energy is nothing but the work done. Another important relation we are going to use in the numericals, so calculations. You must know in the electrochemical cell, so the redox chemical reaction takes place. Chemical energy will convert to electrical energy. How chemical energy will convert to electrical energy? At the cost of free energy. The free energy decreases. When chemical energy has been converted into electrical energy, the free energy decreases. Work done is equal to decrease the free energy. Therefore, so the work done is given by n number of moles of electrons, so this is called the Faraday and the standard EMF of the cell. So the free energy or work done during the electrochemical cell can be calculated. It is another equation. Different forms of the Nernst equation. But another equation, another relation. Look at this. I written here relationship between standard free energy and equilibrium constant. So I will use the same equation. I will use this this equation. The E cell is equal to E naught cell minus 2.303 RTNF log to the base of Kc. We are going to measure the Kc at equilibrium. Means we are carrying out the reversible reaction. As the reaction proceeds, the concentration of the reaction decreases, the product concentration increases. At some time we get an equilibrium. When the equilibrium is obtained in the electrochemical cell, no current flows in the circuit. So this way reactant concentration decreases. The product concentration increases in the reversible redox reaction. When the equilibrium has been attained, when the equilibrium has been attained, so no current flows in the circuit. Therefore, the EMF of the cell is equal to 0. Take EMF cell is equal to 0, E naught cell is equal to 2.303 RT in the log to the case, equilibrium constant. We know this equation delta G naught is equal to minus N F E naught of cell. Substitute the value for E naught of cell is given by 2.303 RT in the log to the base of Kc. The NF and NF will get cancels. We get delta G naught is equal to minus 2.303 RT log to the base of Kc. But again, in this equation, delta G naught is the the work done, or the degree of energy is given by minus N F E naught of cell. So I want to get the value of the equilibrium constant. Therefore, the log Kc was found to be this is the N F E naught cell divided by 2.303. So by this equation, the equilibrium constant of any reversible redox reaction can be calculated. Look at this equation. E naught of cell, equilibrium constant. How they are related? They are the numerator. The more the E naught cell, more will be the Kc. Or the more the value of the Kc, more will be the E naught cell. And this this equilibrium constant mainly depends upon the E naught of cell. Here the equilibrium, it is a multiple choice question. See, a lot of application will do. Here the equilibrium constant. Here is the standard free energy of the cell. Lower the value of equilibrium constant, lower will be the standard free energy of the cell. And this equation can be used to calculate the single electropotential or the EMF of a cell by using the various forms of the Nernst equation I have given. So with this, suppose I have given this equation. This is the E cell is equal to E naught cell minus 2.303 or the product of the products to the reactants. How we can apply this equation? Look at this. I give a simple example of taken. So this is nickel. This is a redox reaction. Nickel is a net reaction here. Nickel solid. So 2Ag plus. So this nickel undergoes oxidation to Ni2 plus. So Ag plus is reduced to Ag. Apply the Nernst equation for this redox reaction for E cell, E naught cell minus 2.303 RT log. So this is the product of the concentration of the products to the product of the concentration of the reactants. Nickel 2 plus concentration, Ag plus concentration, Ag is 2Ag to the power 2 Ag concentration to the power 2. Reactants is nickel solid. So this is Ag plus concentration to the power 2. Just again the equation, So this equation, this is the product of the active mass of the products and the reactant. Apply the same equation. Write the equation here. Look at this equation. So silver solid, So this is taken as the 1. This is taken as the concentration 1. So this is nickel solid is taken as the concentration 1. For any metal solution, concentration is 1. Therefore, it becomes nickel 2 plus air concentration and the Ag plus air concentration. Therefore, the E cell is called E naught cell. 2.303 the RT log to the base 2. This is the nickel 2 plus air concentration. Ag plus air concentration. What is this? So we can measure the EMF of the cell by maintaining these two concentration. If you know metal rod, dipped into metal solution, which concentration? Well, based on this concentration, you will get the EMF of the cell can be calculated. So I have this equation is while writing, I give this equation of product of the active mass of the products with the product of the active mass of the reactants are shown here. But in this equation, for the product of the active mass of the products with the product of the active mass of the reactants are taken. So in this case, if any the solid will come, metal will come, you take the concentration as unity. The same thing I did here. I have taken the Ag solid is taken as unity 1. Nickel solid is taken as 1. Only left with nickel 2 plus air concentration, Ag plus air concentration. Nickel 2 plus, so Ag plus to the power 2. Substitute the concentration. You know the E naught cell. So EMF of the cell can be calculated. These are the various forms of the Nernst equation used to calculate the EMF for a single electrode potential. So with this, all the Nernst equation, I give you what are the differences between electrochemical cell and electrolytic cell. In the earlier period, you have studied the electrolytic cell, you have studied electrolytic cell, and you know what is the inertial flow of current, what is the inertial flow of electron, what reaction occurring at the surface of the electrodes. Even you have studied the Faraday's laws also. I hope you are all familiar with this electrolysis. I discussed on the electrochemical cell. what is the difference between the electrochemical cell and the electrolytic cell? Look at difference one by one. Now, the electrochemical cell means galvanic cell or Daniel cell or contact cell. So this is electrolytic cell where you are going to carry out the electrons. I told you can use a current as a source of energy. We can do metallurgy. We can manufacture metals and the various other compounds. This is the electrolytic cell. What are the fundamental difference between these two? But in this, I told you interconversion chemical energy to electrical energy. I told you apply that. So the electrochemical cell, electrical energy is produced. You are going to carry out a redox chemical reaction, and chemical energy will convert to electrical energy, or the electrical energy is produced here. But here in electronic cell, electrical energy is consumed. They are going to use a current as a source of energy. They are going to pass the current through the cell, and they are going to manufacture useful compounds. The electrical energy is produced here. Electrical energy is consumed here. One important difference. Other most of you are getting confused. Here in the electrochemical cell, but here also the anode cathode will come. Here also anode cathode will come. But sign is different. Be very cautious in this side. In electrochemical cell, so anode means minus. Negative refers to anode, but a positive refers to cathode. That is sure. Look at this. I showed here. Come to this point. Look at this diagram. So this zinc undergoes oxidation. So this is anode is negative. So here this undergoes reduction. Here cathode is positive. So in this electrochemical cell, negative refers to anode, positive refers to cathode. But you go back to the electronic cell, it is different. So this is the positive in form of the anode, negative in form of the cathode. There is a lot of sign difference because here the electrical energy is produced here. Sign is different. Here electrical energy is consumed. You are going to use a battery. We are connected to the anode and the cathode. In the electrochemical cell, so the anode is negative and cathode is positive. In the electrolytic cell, it is reverse. Anode is positive and cathode is negative in the electrolytic cell. Two fundamental differences, so you should not forget. Come back here. Notice the electrical energy is produced. Electrical energy is consumed here. What sign I told you? Anode is negative, cathode is positive. What is reverse in the electronic cell? Positive is anode, negative is cathode. Other important is in electronic cell, we are going to use the salt bridge. For salt bridge is used for this. It is a salt bridge. It is a U-shaped glass tube. Salt bridge is used to give current to off cells. Salt bridge is used, so in the electrochemical cell. But in the electronic cell, no salt bridge is used. You take the same electrode, dip anode and cathode, you have passed the electric current. You are not going to separate anode and cathode in the electronic cell. But here, you will avoid the liquid junction potential because you are going to measure the current here. To avoid the liquid junction potential, to get electrical contact between the two of cells, we are going to use the salt bridge, actually the U-shaped glass tube filled with potassium chloride. Because potassium chloride by here is used, it has got the almost equal rates of aggregation of ions. So these are the K plus ions move towards the negative charges. So Cl move towards the positive charges. These ions in the salt bridge will carry the electric current, give the electrical contact between the two of cells. Because in all electrochemical cells, salt bridge is used. In electrolysis, no salt bridge is used. Electrodes are dipped in the same solution. One more important difference, this is this electrochemical cell, as I told you, it is spontaneous. You know what is the spontaneous? The reaction which takes place on its own without the external agency is called spontaneous. But this galvanic cell is a spontaneous. You set up the galvanic cell. The reaction keep on taking place till the equilibrium is attained. Or when the equilibrium has been attained, no current flows in the outer circuit. A small amount of the anode cathode reaction keep on taking place. So this is spontaneous. But the electronic cell is non-spontaneous. It takes place only if you pass the electric current. If electric current is cut off, immediately the process will stop. So four fundamental differences between the electrolytic cell and electrochemical cell. In the electrochemical cell, electrical energy is produced. In the electrolytic cell, electrical energy is consumed. Sign is different. Here the anode is negative and the cathode is positive. But if you put the electrolytic cell, is different. Anode is positive, cathode is negative. Here the salt bridge is used, but then the salt bridge is not used. So thermodynamically, so this electrochemical cell is a spontaneous process. The reaction takes place on its own, but this will take place only with the help of a current as a source of current. Therefore, the electronic cell is non-spontaneous. Friends, so with this, so the next in the next lecture, I will discuss, I given the single electrode potential. I given the Nernst equation to measure a single electrode potential. How experimentally I can measure a single electrode potential? So we can to measure a single electrode potential, we require a reference electrode. Then what is a reference electrode? How it can be used to measure single electrode flows, single electrode potential. That's what take up in my next class. Thank you, students. Friends, I will explain about the reference electrode. What is the reference electrode? How it can be used to measure the single electrode potential. As I told you earlier, single electrode potential cannot be measured experimentally. Single, suppose I take a zinc rod, depleting sulfate solution. I told you at the junction, the metal and solution, a small amount of current develops, potential develops. I cannot keep on a voltmeter, I cannot measure. How can you measure the single electrode potential? To measure single electrode potential, we require one standard electrode of known potential. So to measure the single electrode potential experimentally, we require another electrode, a known electrode of known potential. And that second electrode of known potential is called the reference electrode. What I will do is, suppose I have taken a zinc electrode, zinc rod depleting sulfate solution. Say so some 1 molar concentration or any concentration. Potential arises here at the junction of metal and the solution. How to measure the potential? To measure the potential, I will use another electrode of known potential. I will take this, say this electrode whose potential is measured every day. Other electrode is electrode of known potential every. I will form a complete cell. Current interleaved with a salt pitch, it will be a copper wire. I will measure the EMF of the cell. Look at this. We know the EMF of the cell. We know this potential. Unknown potential can be calculated. Now EMF is the potential difference between the cathode and the anode. EMF I am going to measure. Cathode and anode, I use one cathode, I use another anode, electrode as known potential. By measuring the EMF of the cell, by knowing the one potential of standard electrode, unknown potential can be, or single electrode potential can be calculated. And that electrode is called the reference electrode. Very commonly, we are going to use the standard hydrogen electrode as a reference electrode. I told you so EMF of the cell is known as potential difference between the cathode and anode. Cathode and potential between the anode. Or E right minus E left. Suppose I take this is the one electrode has been constructed. I don't know this potential. I will take one electrode of known potential. This potential is known for us. I am going to measure the EMF experimentally. So these values will be known to you. We can measure the unknown potential. So to measure the unknown potential, we require another electrode of known potential. That is called the reference electrode. I will take the unknown potential whose value is determined is taken, is clubbed with the one standard electrode of known potential. It forms one electrochemical cell. So measure the EMF experimentally. I know the EMF value. I know this potential, standard potential. So this unknown electrode potential can be measured. That is called the reference electrode. So second electrode of known potential is called the reference electrode. Very commonly, but standard hydrogen electrode is used as a reference electrode. How this electrode has been constructed? I will give the diagram. Look at this diagram. So very commonly this question appears, 99% most of the question paper, write the diagram, labeled diagram of standard hydrogen electrode. It's a very common question. So this hydrogen electrode consisting of a glass tube. I will take a glass tube. So this is the inner glass tube. And here a platinum wire is used, a copper wire is used. At the bottom, a platinum foil is used here. A platinum foil coated with platinum black, means platinum oxide, to make the surface rough. So this is platinum foil, dry platinum foil coated with platinum black. This is a inner glass tube. So this is a platinum foil coated with platinum black or platinum oxide is fused to the inner glass tube. So this inner glass tube is surrounded by an outer glass tube. So this is surrounded by outer glass tube, and there is a small side tube almost at the top. So this is the outer glass tube. A small hole will be here, a small hole. So this is the outer glass tube. So this inner glass tube, a bright platinum foil coated platinum black is fused. So this inner glass tube is surrounded by the outer glass tube. And this the electrode is dipped into 1 molar HCl solution, hydrochloric acid. Means unit H plus ion concentration consisting of unit molar concentration H plus this dipped into 1 molar HCl solution. Yes, we are going to maintain some standard conditions. So this you have taken 1 molar H plus HCl, any solution of 1 molar H plus ion concentration. So here what I do, I pass the hydrogen gas. The purified hydrogen gas is bubbled through the electrode exactly at 1 atmospheric pressure. Now here the standard electrode, so many conditions are maintained. So here I am going to pass the hydrogen gas exactly at 1 atmospheric pressure is bubbled through this solution. This electrode is dipped into 1 molar hydrochloric acid solution. So here what happens so this hydrogen gas bubbles passing, they are absorbed by the platinum black. Is in contact with the H plus ions in this solution. Some bubbles may escape like this. Some bubbles will escape through the holes, or some bubbles will escape like this. Escape of the holes. Some bubbles may escape. Continuously you are passing the hydrogen gas exactly at 1 atmospheric pressure. Here what happens? Hydrogen is in contact with H plus ions of this solution. The same principle of the single electrode potential. Any metal rod dipped into a metallic salt solution contains its own ions. Hydrogen is a gas, I cannot dip the gas. So what happens? This is platinum is used here. Platinum is used, and the platinum hydrogen gas is absorbed, and this hydrogen is in contact with the H plus ions. So this is the electrical double layer takes place, and a potential is developed. How much potential is developed? I told you single electrode potential can be measured experimentally. How to fix the potential for this electrode? Look at the some assumptions have been made in scientific studies. I'll give you a simple example. See, we are going to measure the height of the mountains. A simple example. Say I have taken the Ooty, Udakamandala. What is the height? We say it is 5,000 feet high or 10,000 feet height. From where it is 10,000 feet height? You can tell the students. It is from sea level. We take sea level as 0. Corresponding to measure the height of the mountain or height of the place. If I go to Bati in Davangere, say it is 300 feet height. From where is 300 feet height? Not from Davangere, not from Haryana. It is from sea level. We take sea level as 0 and they are going to measure the height of the mountains around of the places. Similarly, and here the standard some other example is another simple example is how atomic weights are expressed. To express atomic weights, you take a carbon 12 as the standard. So using carbon 12 as a standard, related to carbon 12 we measure the atomic weights. That is sometimes you assume the standards. Related to the standard, you are going to measure the other property. See here, so you have taken so hydrogen gas is bubbled through the solution. Hydrogen gas is absorbed on the platinum black, is in contact with H plus ions of the solution. So this is the hydrogen gas is absorbed in platinum black. Hydrogen gas is in contact with H plus ions in the solution. So this electrode reaction takes place. 2H plus 2E. And this electrode reaction takes place. And this electrode reaction takes place. The electrical double layer is formed here, and a potential is developed. How much potential developed we don't know, because if you use the standard, the potential of this electrode is arbitrarily taken as 0. So this can be used as a reference electrode to measure the unknown potential. I give the example of sea level. We take sea level as 0, and we are going to measure the entire mountains because we have to measure the single electrode potential. We require one electrode of more potential. We can't measure it directly. We maintain some standard conditions, standard hydrogen electrode, but here the platinum foil is dipped into the unit molar 1 molar H plus ion solution concentration, and hydrogen purified hydrogen gas. This gas should not contain any impurity, will poison the platinum. So pure hydrogen gas exactly at 1 atmospheric pressure is bubbled from this solution. The hydrogen gas absorbed the platinum is in current H plus ion, electrical double layer takes place and potential is developed. How much potential we don't know. So arbitrarily the potential of this electrode is taken as 0. Using this as a 0, we are going to measure the potentials of other unknown electrodes. Suppose I give an example, say the potential, static potential of zinc electrode was going to be minus 0.76 volts. We measure experimentally because we take a hydrogen electrode 0, corresponding this is 0. Zinc has got minus 0.76 volts. Or take the potential of copper electrode, E naught of copper was going to be plus 0.34 volts. This is against hydrogen electrode. And that way, so the unknown electrode is taken. So then the unknown electrode is taken. So take unknown electrode. And you take the electrode, hydrogen electrode, you form an electrochemical cell. So measure the EMF of the cell. So knowing the EMF of the cell, knowing this potential of hydrogen electrode, unknown potential can be calculated. And this electrode can be represented. Take on the platinum, this is the platinum hydrogen gas is absorbed at 1 atmospheric pressure, is in current H plus ions, whose concentration is 1 molar concentration. This is the electrode representation, electrode reaction, electrode representation. So this electrode, is a reversible electrode. It can undergo oxidation. It gets undergoes H2, decomposes into 2H plus 2 electrons. It can undergo oxidation or reduction depending on the other electrode. This is a reversible electrode. So hence, the potential of this electrode is arbitrarily taken at 0. Using this as a standard. So this electrode can be used as a reference. Very common question in board examination, and the concept has to be carried out. The potential of this hydrogen electrode is arbitrarily taken as 0. The same concept has been employed. Metal rod is in contact with metallic salt solution. So at the interface of the metal and the solution, the potential is developed. We also have taken the platinum foil, rough surface. We are passing the hydrogen. So hydrogen gas bubbles is in contact with the H plus acid solution. When this electrode reaction takes place, there is a formation of different double layer. Potential is developed. How much potential developed? We don't know. That's why the potential of this electrode is arbitrarily taken as 0. And this is used as a reference electrode to measure the unknown electrode potential. So this, the electrode is very difficult to set up because you have to pass hydrogen gas. That means you have to generate hydrogen gas. Hydrogen gas has to be purified. It should not contain any carbon monoxide or hydrogen cyanide. They will poison the platinum. Its equilibrium will be altered. The pure hydrogen gas to be taken is passed exactly 1 atmospheric pressure. Throughout the experiment, you have to maintain 1 atmospheric pressure. And this is the concentration H plus ion should be maintained at the 1 molar concentration. And your solution should not contain any oxidation and reducing impurity. You have completely destroyed this equilibrium. With all this, the difficult condition, this electrode is constructed and used as a reference electrode to measure the unknown single electrode potential. But actually, we come across secondary reference. This is a primary reference electrode. So with this, the primary reference electrode, some other electrodes have been constructed. They are very easy to set up, like glass electrode, so twin hydrogen electrode, and even the number of electrodes like caramel electrode, glass electrode, twin hydrogen electrode. Number of electrodes set up. They are very easy to set up and simple to operate. They are called secondary reference electrode. Those secondary reference electrode has been standardized using this electrode. Whenever you want, for every year, you can go for secondary reference electrode. But study of those secondary reference electrode is not there in the NCERT syllabus. You forget it. You don't have the secondary reference electrode like caramel electrode, glass electrode. They are simple. Within 1 minute, you can set up those electrodes. Whenever you want to use the second reference electrode, because if you want to go for hydrogen electrode, so many conditions you have to maintain. You have to get your hydrogen gas, condense supplied at 1 atmospheric pressure. So throughout the experiment, you have to maintain the unit molar concentration, H plus ion concentration. So this should not contain any impurity, reducing impurity, oxidizing impurity, poison molecule. With all this difficult condition. Anyway, with all this condition, since you don't have a second reference electrode, you consider all the difficult condition, this potential, this electrode has been constructed. and whose potential is arbitrarily taken as 0. I am repeating, because to measure the single electrode potential, we require one more electrode of known potential. But electrode potential cannot be measured. Just I gave the example of C level is 0 and the mountains are measured. Atomic measure expressed later to the carbon dollar scale. We will use some standard. That's why. So this electrode has been constructed. So this electrode reaction takes place. The potential, there some potential develops here, and the potential developed is arbitrarily taken as 0. You see, this is 0. So this electrode can be used as a reference electrode to measure the unknown electrode potential. Okay, student friends. So in the next period, I will continue how this electrode can be used to measure the single electrode potential. So based on that, we have studied the electrochemical series. Electrochemical series has been framed because the number of metals are available, elements are available, and you have to measure the single electrode, standard electrode potential, and you are going to use addition electrode as a reference electrode to measure the unknown electrode potential. This is called the reference electrode. Standard is called the SIG, standard addition electrode is used as reference electrode. The potential is normally taken as 0. So this potential, this electrode is used as a reference electrode to measure the unknown electrode potential. Okay, friends? Okay, I will continue with the next slide. Thank you.
Subscribe now and press the bell icon. Never miss an update.